Hello all. Let me brief you on one of the coupling reactions in which a palladium catalyst is involved, or an organopalladium catalyst is involved, and that coupling reaction is Suzuki Miyaura coupling reaction. We have other coupling reactions too, wherein palladium catalyst is involved, like Heck coupling reaction, Still coupling, Negishi coupling, etc. Okay, now before we go into Suzuki coupling reaction, let's see what a coupling reaction is. Now, as the name suggests, coupling reaction is simply bringing together two organic fragments. Two organic fragments are joined together, and in this case we are carrying out this coupling with the help of a transition metal catalyst. And here the transition metal catalyst is palladium. And the substrates which is used for the coupling reaction is an organometallic compound and an organic halide. Alkyl or aryl or allyl halide, organic halide. And these two come together in the presence of a transition metal catalyst, and you get the coupled product. It can be it will be a different organic compound. So a CC bond is formed during coupling reaction. Now, depending upon the metal on the organometallic compound substrate, we have got different coupling reactions like Negishi coupling, Hiyama coupling, Still coupling, Sonogashira coupling, etc. Okay. Now, let us go into detail into Suzuki coupling, Suzuki Miyaura coupling reaction. Now, before we go into detail into Suzuki Miyaura coupling reaction, let us see the general catalytic loop of a coupling reaction. For any coupling reaction. Okay, so for any coupling reaction, the general catalytic loop is having 4 steps, or oxidative addition, transmetallation, cis-trans isomerization, and reductive elimination. In oxidative addition, the organic halide is added on to this palladium nickel or palladium catalyst. Or you can say the nickel or the palladium catalyst is getting inserted between the organic moiety and the halogen group in the organic halide. So you can see here a sort of insertion, oxidative addition, and the oxidative state of the palladium or the nickel catalyst is changed from 0 to 2. 0 to plus 2. Then is the transmetallation step, wherein the organic group from the organometal compound is transferred to the palladium or the nickel. So from one metal to other metal. And in cis-trans isomerization, a simple rearrangement of the alkyl groups or the organic moieties, and then reductive elimination, wherein we get a coupled product. In detail, you just go and you just check out my videos on the first video, that is on Negishi coupling. I've explained a bit more regarding this catalytic loop. Now coming to Suzuki coupling. Suzuki coupling was published in 1979. Okay, Suzuki Miyaura coupling reaction was published in 1979. It was one among the series of coupling reactions published with the development of the palladium, organopalladium catalyst. Okay. Now, this particular coupling reaction happens between organoboronic acid and halides of aryl, alkyl, alkenyl or alkynyls. Okay, so aryl halides, alkyl halides, alkenyl halides and alkynyl halides can be used for coupling with organoboronic acid or organoboranes. And in the presence of palladium catalyst, we get cross-coupled product. Okay, so one example here, we have here the alkyl halide, okay, and you have the organoborane over here. Now the organic moiety on the organoborane can be aryl, vinyl or alkyl. You have the palladium catalyst here, okay, and you get the higher order alkane. Okay, this was published in the year 2002. Okay, alright, so that is one example for Suzuki coupling reaction. Now, the Suzuki coupling reaction is preferred because of the stability, ease of preparation, and low toxicity of boronic acid compounds. Okay, so boronic acid compounds are stable, easy to prepare, and low in toxicity. Therefore, the Suzuki coupling reactions are preferred for coupling or bringing together two organic moieties or for carrying out CC bond formation. Now, one particular thing, we can use different organoboranes for this reaction. Potassium trifluoroborates and organoboranes or boronate esters can also be used. So, this is the boronic acid structure. This can be used. Another borane is organotrifluoroborate. Okay. Another organoborane which can be used is pinacol boronic ester, or we can even use 1,8-diamino naphthyl boronamide. Okay, so all these organoboranes can be used, and these are the usually used boranes for coupling in the Suzuki coupling reaction. Okay, boronic acid, organotrifluoroborate, pinacol boronic ester, and 1,8-diamino naphthyl boronamide. Now, another example here, we have used boronic acid and an aryl halide, and you get a biphenyl. Okay, boronic acid is used, aryl halide is used, and you get a biphenyl. Okay, this was published in 2016. So, you can see that this is still a live area of research going on, coupling reactions. Okay. Another example here we have used is vinyl halide. Okay, again boronic acid as the organoborane, and you get a coupled product over here. Okay, so here in the vinyl halide, R can be alkyl, phenyl, another vinyl group, or COET group. All right, and you get a coupled product over here. So this was in 2000. This was published in 2012. The reaction was published in 2012. So various synthesis is being carried out even now for coupling reactions. That means the coupling reaction is still alive. I mean, the reaction has not been finished yet. You can still carry out research on it. All right. Now coming to the catalytic loop of Suzuki coupling reaction. As any coupling reaction, Suzuki coupling reaction also has the same oxidative addition, transmetallation, and reductive elimination step. Now here you can see the oxidative addition step over here. The palladium is getting inserted between the organic halide, and the palladium oxidation state changes from palladium 0 to palladium 2. And here, one thing what you have to remember is, in case of vinyl halide, the oxidative addition proceeds in retention of configuration, while in case of allylic and benzylic halide, there will be an inversion of configuration. Okay, so oxidative addition involves retention of configuration in vinyl halide, while in case of allylic and benzylic halide, it involves inversion of stereochemistry. Okay, and here you have the transmetallation step. Now one more thing, we have a base here, sodium tertiary butoxide base is here, and this particular reaction will not proceed in the absence of a base. Now the role of base is to activate, one role of the base is to activate the boronic acid, and this facilitates what you call the transmetallation step. Now here, initially what the base does is it will abstract this halogen part from the oxidative addition product, and the anion of the base gets added on to the palladium. Okay, anion of the base gets added up to the palladium. And also, the base, another mole of base gets, activates the boronic acid. The anion of the base attaches to the boron, attaches to the boron of the organoborane and increases the nucleophilicity of boron. Okay, it increases the nucleophilicity of boron. And see here you can see the borane, once the borane is being reacted with this palladium organopalladium compound, you get to the borane two butoxide ions, one from this palladium, one from this base. Alright, so Suzuki coupling will happen only in the presence of a base, and the role of the base is to activate the boronic acid, and the activation of boron atom enhances the polarization of the organic ligand and facilitates transmetallation. The anion of the base gets attached to the boron of organoborane and increases the nucleophilicity of boron. And this will help the easy leaving of the boron during the transmetallation, boron group during the transmetallation step, and you get almost the two alkyl groups linked to the palladium. And coming to the reductive elimination part, this reductive elimination part moves on, proceeds with retention of stereochemistry. Okay, so here you have to remember, reductive elimination proceeds with retention of stereochemistry. That means whatever was the stereochemistry during the oxidative addition, the same stereochemistry is maintained over here. So in the case of vinyl halide, always we will get a retained product. And in case of allylic and benzylic halide, we get an inverted product. Okay, and also the reductive elimination depends on the strength of the carbon-carbon bond formed. If a carbon-carbon bond formed is stronger, faster will be the reductive elimination, and so biaryl compound will be faster than aryl-alkyl coupling and alkyl-alkyl coupling. Okay, so these are the this is the mechanism involved in Suzuki coupling. Now we'll see once more, just to brush up once more. So in oxidative addition, it proceeds with retention of stereochemistry in case of vinyl halide and inversion of stereochemistry in case of allylic and benzylic halide. Okay, and transmetallation step proceeds with in the presence of base, and the base activates the boronic acid, and the activation of boron atom enhances the polarization of organic ligand and facilitates transmetallation step, and also it increases the nucleophilicity of boron. Alright, and our reductive elimination proceeds with retention of stereochemistry. It depends upon the CC bond strength. Stronger the bond form of the coupled product, faster will be the reaction. So this particular product formed, this particular reaction wherein two aryl groups are coupled will be faster than a coupling of aryl and alkyl or alkyl and alkyl group. Now let us see a few examples of Suzuki coupling reactions. Suzuki coupling has been frequently used for synthesis of complex compounds, particularly natural product compounds. Okay, like synthesis of caparatriene, which is a natural product, is used. We can carry out the synthesis using Suzuki coupling, and this is carried out from citronellal. Okay, and this particular compound, caparatriene, is very active against leukemia, for treatment of leukemia. Similarly, a lot of synthetic applications are there for the synthesis of polyolefins, styrenes, and substituted biphenyls. Now let us see the preparation of or synthesis of caparatriene. Now here we have the reaction for the synthesis of caparatriene. See, we have the citronellal here. Initially, in the first step, citronellal is converted to its boron derivative. So it's treated with the catechol borane, and then it is the citronellal is converted to the boron derivative, and then this boron derivative is treated with this halide, and you get the caparatriene. So here you can see the bond formed. So this after this double bond, we have the boron compound. This boron moiety, this boron moiety is replaced by this particular halide wherein this bromine is removed. So it is at this point of it is this carbon which is getting attached to this carbon on the borane. So that simple CC bond formation is done here. See the simple this CC bond formation, and that can be easily done using Suzuki Miyaura coupling reaction, and the base used here is sodium ethoxide. Okay, so it is here in the second step that we are using Suzuki coupling. Okay, in the first step it is the preparation of your formation of the boron compound, borane, organoborane, and it is in the second step that we are carrying out the Suzuki coupling reaction for the formation of the para-triene. Similarly, we have another compound called A86929. Okay, this was communicated published in 2013. It's a recent research. So here, this particular compound is a dopamine agonist. Okay, dopamine, again, it works against dopamine. Alright, so here you can see this alkyne compound, aryl alkyne compound, and we have the boron compound. And these two come together to form this intermediate over here. Okay, so this boron compound and that's alkyne compound come together and form an intermediate. Another organoborane is formed over here, and it is at this intermediate and this hetero compound. See this hetero compound which couple together to form the compound, the dopamine D1 agonist A86929 compound. So it is here that our Suzuki coupling is happening. Okay, so in the same way, in para-triene also the organoborane was formed in situ. Similarly, we are forming the organoborane in situ, and this organoborane then undergoes coupling reaction in the presence of palladium catalyst, palladium triphenyl phosphine, tetratriphenyl phosphine compound. Okay, so that's one. So this is the intermediate form. So at this alkyne part, the boron gets attached, see here, and then to this alkyne group, now this has become alkene, and to this carbon our heteroatomic compound gets attached. So sort of we can say activation of this site or something like that, but the coupling happens at this end and this one. Okay. So that's a coupled product. Another example is synthesis of KDR kinase inhibitor. This involves CN coupling. Earlier we said it is CC coupling. Here CN coupling initially. I don't say that Suzuki coupling results in CN coupling, but here initially a CN coupling forms and then our CC coupling happens. So in KDR kinase inhibitor, enzyme inhibitor, first what happens is the amino group on this compound attacks on this double bonded carbon atom and one halogen is lost. Okay, this halogen is lost. So you can imagine this as the five-membered halide is formed with bromine over here. This then couples with the boronic acid, borane, organoborane. And at this boron carbon, this carbon to which the boron moiety is attached, that couples with the carbon to which the halogen is attached. So that's here. So we get this five-membered ring initially. Okay, so that's tandem CN coupling. CN coupling happens first, and then one halogen will be remaining over here. That halogen is removed and this boron moiety is removed, and this carbon couples together. CC coupling happens. Okay, so here is the palladium catalyst which is involved. This is the Suzuki coupling reaction happening. Okay, so these were the two synthetic applications and the mechanism of Suzuki coupling reaction, which involves what is called the organopalladium catalyst. Okay, please do watch my other videos on coupling reactions too, Miyaura coupling and Negishi coupling and also Kumada coupling. Thank you for watching this video. Thank you.